I'm Thanasis from University of Athens. The main challenge is that we want to execute analysis on data from several hospitals. Algorithms like machine learning or whatever else you can imagine. The main problem for this is that hospitals have a real sensitivity on their data. They don't want the patient data to be touched at any way, leave the hospital. So they are very sensitive on that. So how can you execute an algorithm on, let's say, 3 hospitals with all of the data combined? So the solution that we created is that we break the algorithm in local and global steps. The local steps are executed on the hospital that contains the data locally. And then we have the engine that aggregates, the local steps after it makes some computations on the data. It sends on the engine some aggregate information, but not the actual patient data. Then the engine aggregates all these results and provides them as input on the global execution step. The global execution step is actually the global execution step, its role is to gather these aggregates, make some further computation, and then produce the actual output of an algorithm. We have 3 types of algorithms: a local global, a multiple local global, and the iterative. So let me elaborate. The local global execution step is, as I said before, we have the local steps that you can imagine. The local ones are actual hospitals with patient data that cannot be, let's say, accessed by an outsider. We have installed the software on the local nodes, and we run the local steps that it touches the executions, that it touches the patient data. They send the aggregate information on the global node, and then with some further processing, it produces the output. Although on most algorithms, on most complex algorithms, the algorithm cannot be recreated in a local global manner in just one local and global step. It needs more than one. So the multiple local global execution is actually the same as the previous one. It has the local hospitals, and then it runs on the global. It runs the global execution step, but then the global step, after it makes some computation, it feeds the local nodes again with some extra information, and then using the patient data and the extra information from the previous step, it further on continues with the algorithm execution. At some point, it can be more than 2 steps, local and global steps. The global node produces the output. We also have the iterative solution, which is basically the same. It has local and global steps, but at some point you have a condition deciding if the output is the final one or not. So when it's the final one, it stops the execution. So how do we create the federated algorithm? As we said before, we have the implementation on local and global steps, which is actually Python code. We have a common library that's assisting with that coding to fetch the data from the database of the hospital. And we have some code defining how the aggregation is done from the different hospitals, gathering the data and providing it in the master node. And we have also a properties file defining the input and the output requirements of the algorithm, so it can be integrated into the engine. So, a problem with that approach is that, as you can understand, an algorithm is a bit complex. It's not so easy just to change the algorithm. So, what we did about that is that we allowed, we created the workflow engine, which is basically it offers customization on the federated algorithms. The federated algorithms is something difficult to change. So you have the workflow engine, which is basically, it allows the users to combine specific algorithms as building blocks to create a bigger workflow, let's say. For example, the PCA, Principal Component Analysis, can be used as a first step to reduce the dimensionality of the data, and then the output is fed to an algorithm such as linear regression. On the workflow engine, when we have a new federated algorithm, we integrate it into the workflow engine. Then we create different, let's say, visualization techniques for that algorithm's output. And then, of course, the end user on the platform can easily customize and choose how he wants the workflow to be shown or created. This is an example of the workflow engine that you have the input on the left column. On the middle, you have the algorithm components, and then on the right, you have the visualization technique. Here we have the available tools, and you can use them to create something different. And this is accessible on the platform for the end user to create. It's usually, let's say, a researcher. It has an extra role, but it is available on the platform. So the medical informatics platform has, let's say, two streams, the downstream and the upstream. What we discuss now is the upstream. How, when you have the data, how do you provide them to the user, and what analysis can you do on them? We also have the downstream, and the downstream is going to be explained by Kostis.
Okay, thank you. So, Thanasis presented the upstream, yeah. It includes all the data analysis, the algorithms that the researcher does on the platform. Now, in order to have all data prepared, ready, and imported into the MIP, we have the downstream, which is actually the data factory. Now, what's the problem in general? The problem is that we have several data sources from different hospitals, okay? And as we all know, heterogeneity is the main problem. Now, we have to integrate all these into a global schema that MIP actually uses for its analysis. Now, on top of that, right now, in the MIP, we have more than one global schema. Why? Because we support analysis on more than one medical conditions, more than one pathologist. So we have several data models. So that's the problem, and the process is referred as data integration, which is the solution to this problem. And that, okay, that happened again. It's something about the cable, I don't think it's... Hmm? Okay, let's go back. Back. There we are. Hospital data integration. Okay, so the steps of the data integration, the three steps, the big steps are these ones. First, we capture the data, okay, from the hospital data sources, and we store them. We store data in a relational database. And then we have to harmonize, as we call it, which is transform the variables values so as to conform to MIP's rules and regulations. Let's say they have to use the correct measurement units, they have to use the correct, have the correct scoring ranges, enumeration values, and all things like that. And then we anonymize so as to be accessed and analyzed by the federation node. Now, a strategic decision on that data integration process of ours was the usage of the I2B2 relational schema, which is used in other projects as well. And it has the ability to actually store data clinical data with varying varying schemas, as long as they are oriented towards the patient visit and clinical observation concept. Meaning if these are their main entities, we can actually import them, map and import them into this I2B2 relational schema. So that's a key feature. From whatever hostel data we have, we import them into a relational database with the schema. Yeah. So whenever we have columns that actually correspond, variables that actually correspond to this schema, we just map them straight ahead. And whenever there is no such corresponding entity variable, we do a trick, which is the unpivoting, meaning storing them in attribute type value tuples. We unfold them somehow. So and we store them in the central table of this database. I'm not sure if that's really clear. I'm going to show you a video, then I guess it will be more clear. So the task is to have a hostel local data schema and a target schema, and the task is to define all the correspondences, all the mappings, all the transformations. And when this is done, we have a mapping task, which we call it a mapping task, which is the whole configuration, the whole how to go from one database to the other. And when this mapping task configuration is done and created, it is actually an XML file. And MIPMaps engine translates this file, and it generates the target database, the target dataset. So yeah, the MIPMap is our main tool, our ETL tool, schema mapping and data exchange tool, which we use in order to do that. So I have a small demonstration of the video. Let me just play it locally because it's better this way. Okay, so this is the graphical interface of our tool, our ETL tool, MIPMap. As I said, on the left we have the source schema, which in that case it's some CSV files, right? Of course, more than one CSV, as many as we want. And on the right we have the target schema, which we want to create. And as I said before, we use the I2B2. So on the right side, it's a relational database, right? Okay. Yeah, okay, there's the ability. Sometimes there are some tables on the right that we don't have something to map to, so we don't have information to send, so they're just going to leave them blank and just shrink them. We don't want to have them to be shown since we're not using it. Now, the simplest case, of course, is to draw lines when we have one-to-one mappings, right? One-to-one correspondences. So this is the simplest case, of course. There are some variables on the left side that have an equivalent variable on the right side. We just map them immediately. So I'm moving on this point. And then, of course, there are some more complex situations, cases, let's say, where we have to map a variable from the left side, but we have to transform its value. Okay, so we use the mapping functions. MIPMap has many mapping functions, transformation functions, which we can use. Now here we just double-click on this function, and we choose from drop-down list the function that we need to use. In this particular case, we use the toDate function, which actually defines the date format, so as to know in which format we store our data on the relational database, which is a pretty common mistake. Sometimes we store dates in wrong format and we are in trouble. Yeah. what else? Of course, yeah, let's say this one, the selected one, may be mapped to more than one variables on the right side because it gives its value to more than one variable on the relational database. This is totally legal as well. Yeah, what else? Now, the thing is, sometimes, as we see, the table on the right takes input from two separate CSV files. So what we need to do in that case, we have to align which tuples, which data it actually takes, meaning we have to join the two tables on the left side. Okay, so MIPMAP also has this feature. You can join tables, okay, to combine the information. Yeah, okay. There are also other features. Let's say there's also selection condition feature from the left side and other things. I'm just showing you the most important ones, the basic ones. Now, okay, and also we also did the unpivoting, which I talked about before. Unpivoting, taking values from the left side and unpivoting, unfolding them into attribute and value tuples on the right side. We use, as I said before, these mapping functions, which of course they may also have more than one input from the left side. And yeah, that's pretty much it in general. And once we have completed this mapping test design, the MIPMAP engine takes this XML configuration, as I said before, and it generates a database as it has been designed. Now let me go back to the presentation. Okay, this is, again, are we good? Yeah, we're good.
It's your empty slide, I think.
Empty slide? No, I don't have an empty slide, but sorry. Okay. And also, we have another, the last thing I want to show you is the data catalog. Now, in order for someone to log into the MIP platform and do some experiments, some analysis, he has to know what data, each hospital, what kind of data it has, descriptions, semantics, and all this. So we have a catalog, if I may, where all this information is gathered and shown. And let me show you the last video. Okay, so as I said before, we have in the MIP many pathologies, and the user actually logs in, chooses the pathology that he's interested in, then he chooses the hospital and searches for the data, searches for the variables that the researcher is interested in, I don't know. Yeah, he can see also the correspondences in this page, how the local variables correspond to the global schema that the platform uses, MIP uses. Also see some statistical reports on the data sets. And pretty much it's an informative platform, this, okay? Just to log in, search. You can also see the whole taxonomy of the data model, so as to know how the variables are grouped, and yeah, moving on. And in the end, okay, search on the taxonomy graph, yeah. And in the end, if the user is authorized by the platform, he can also add some new metadata version. So, yeah, that's pretty much it. And okay, so in the end, we have two pictures, two figures, one of the generic, of the high-level architecture of the whole MIP, and the other one is a figure of the data factory pipeline, which also includes some other tools which I have not talked to you yet. Not yet, I won't talk to you today, but if someone wants, I will talk to you in person, such as the quality control tool, let's say. And Thanasis will show you.
Yep. As a final thing, to show you an example of the MIP platform as it looks today on the QA environment. Yep. Okay, so we can see here that this is basically a visualization of the data that Kostis talked about that the hospitals have. On the datasets, we have different datasets that on the production environment would be different hospitals, for example. We can choose the variables here, and we can, on the right, we can see a histogram that is actually run on a federation way, gathering the information from all the different hospitals. And we can run an algorithm, for example, Pearson correlation on all of these datasets. And this is actually executed on all the hospitals. Then it makes some local global steps. And then at the end, we're going to see a visualization of the Pearson correlation, which is a heat map showing the correlation between the variables. This is the Pearson correlation experiment, let's say, algorithm. And we also have, let's say, linear regression, ANOVA, and other algorithms. Yep. Thank you.
Okay, we have some time for questions. Maybe I start again. So, from the technical point of view, regarding the ensuring that this local and global view on the data is somehow split into a private part, which stays at the hospital, and then the global part, which is communicated in an aggregated way. So how do you...
It still stays at the hospital, right, Thanasis?
Mm-hmm.
So how do you implement this technically? So I think of, at some point, maybe the local code has to be changed, or the implementation of the services. Is there some code review? Is the deployment somehow authorized?
Yeah, of course, all the algorithms that are run on the federated engine, let's say, is of course approved, let's say, by someone behind the scenes that checks if the algorithm is created on a privacy compliant manner. If, as we said, the local execution steps that do not send, for example, information on the outside world, and it sends only aggregate information. The global step is just receiving the information from the local steps and makes more computation. The global step is, let's say, on the outside world. We can do whatever we want and send whatever we want. But we only receive aggregate information, never patient data.
Okay, good. And I also have a second question. So these graphs, I saw that you have basically this I2B2 thing on top of Postgres or something like this, approximately. So does this, I mean, there's a lot of metadata involved. Is this already linked to the knowledge graph data structure? So can you...
To the knowledge graph?
Yeah.
No, that's on the to-do list right now.
Okay.
But
So
we don't have
I think of
link to a graph right now, to a knowledge graph.
Yeah, I just think of, I mean, if you have, for example, models that work on this aggregated data, and you basically, I mean, you have this nice small demo here, and you have some complex analysis. I mean, this could be already interesting in the
Yeah,
knowledge graph
indeed,
effect,
it is interesting, yeah.
Okay, other questions?
Okay,
Okay, then
thank
thank
you.
you again.